In our discussion of inductors thus far, we have neglected the resistance of the windings, but every inductor found in the real world must have some resistance unless its windings are superconducting. So we can represent a real-life inductor as an ideal zero resistance inductor with self-inductance L in series with a resistance R as shown. So here's the resistance R and the inductance L. So this diagram can also represent a resistor in series with an inductor. In that case, R is the total resistance. This circuit shows some interesting behaviour by means of switch S1 here and switch S2. The RL combination can be connected to a source with constant terminal voltage V, or it may be shorted by closing S2. Suppose both switches are initially open as they are, and then at some initial time t equals 0, switch S1 is closed. Because of the self-induced EMF in the inductor, the current does not immediately rise to its final value at the instant S1 is closed. Instead, it grows at a rate that depends on the values of R and L in the circuit. Let little I represent the instantaneous current at some time t after the switch is closed, then di by dt is its rate of increase at that time. The potential difference across the inductor then is VCB L di by dt. So across here, the voltage drop across there is VCB L di by dt. And the potential difference across the resistor is IR. V, the total voltage, is this voltage plus this voltage, and that equals the source voltage. So the source voltage will equal the voltage across there and the voltage across there. It follows that we can plug these values in then, and we can rewrite it as V equals L di by dt at IR. The rate of increase of current is therefore, we can rearrange this, bring the L on this side and the IR on this side, and we end up with di by dt equals V minus IR over L. Bringing the L out, so it's V over L. We can then rewrite this as V over L minus R over Li. So that's our equation for the rate of the current changing. At the instant the circuit is first closed, I equals 0. We end up with the initial, when I equals 0, the rate of increase will be at its maximum, which is V over L. The greater the self-inductance, the more slowly the current increases. As the current increases, the term Ri over L increases also. Hence, the rate of increase of current becomes smaller and smaller. When the current reaches its final steady state value, its rate of increase is 0. So if you put 0 there, rewrite it here, that then is there, this one, going down to there, and that becomes I equals V over R, which is the same as if there's no inductance at all at that point. To obtain an expression for the current as a function of time, we proceed just as we did for the problem of the charging capacitor example. So first of all, we'll rearrange this 2 equation. We'll bring the di's all on one side, and we'll get the t's on one side. And then once we've integrated both sides, these are really easy integrals. You know that the integral of 1 over something is log. So we get log V over R minus I. Now on this side, RL dt, so obviously that is going to just be RLT plus constant. So we end up with this equation here. The integration constant is found by noting that the initial current is 0. So I equals 0 at time t equals 0, so the constant then obviously equals, if you plug in t equals 0 there and I equals 0, you just end up with minus LV over R equals constant. So that's our constant value, minus ln V over R. With that, we can insert constant back into this equation. So we now end up something a lot easier. We end up with minus LV over R minus I equals R of this equation here. We'll just swap the signs around to make that easier to manipulate. Then of course once we've got to here, we can just use standard log laws. We know that the log of a number minus the log of another number is the same as making that the numerator and that denominator. So we've got ln that, and then of course we can tidy that up a bit. We'll end up with this, and now you know that the natural log of a number is the power to which the base being e here must be raised. So then that is that number in there is going to be e raised to that, so we can draw that right down. 1 minus r over vi equals e to the minus this term. Then it's just a matter of rearranging it for I. So eventually, if you just rearrange this in terms of I, you can write that down. So now we have what we're after. We've got an equation here which will give us the current as a function of t. We can plug in any value of t here and get our current value. If we differentiate that with respect to time, we can also then, of course, get the rate that the current is changing. So by doing that, we end up with this equation, v over L e to the minus RLT. So from equation 4 and 5, we know that at time equals 0, I equals 0, and di by dt equals v over L. As t approaches infinity, looking at equation 4, you can see as t approaches infinity here, we're going to get I equals v over r, exactly as we previously showed. So that proves that this function is completely valid to describe this circuit. So with that, figure A here is a graph of that equation, this equation that we ended up with. It shows the variation of current with time. The instantaneous current I first rises, so it first rises very quickly, and then increases more slowly as it approaches the v over r part. Our time t equals L over r. If we put L over r for t here, we end up with e to the minus 1, which is 1 minus 1 over e, and that value then becomes 0.63 of its final value. This time is called the time constant, or the decay constant for the circuit, and it's written as L over r. So for a given value of r, the time constant increases when the inductance L increases. Thus, although the graph of I versus t has the same general shape, whatever the inductance, the current rises rapidly to its final value if L is small, and slowly if L is large. So it's always going to get to this value, but depending on what the L value is, it's going to get there faster or more slowly. So it's always going to be this shape, but it might, for example, it might go up there and round there, or it might take a long time and before it reaches there. For example, if R equals 100 ohms and L equals 10 henries, then L over R equals 0.1 seconds. So we've got an example there. And the current increases to about 63% of its final value in 0.1 seconds. But if L equals 0.01 henries and L over R then equals 0.01 over 100, it's 10 to the minus 4 seconds, so it's much quicker. So only 10 to the minus 4 seconds is required for current to increase to 63% of its final value. Energy considerations offer us additional insight, so we're looking at this, into the behaviour of an RL circuit. The instantaneous rate at which the source delivers energy to the circuit is P equals V times I, joules per second. The instantaneous rate at which energy is dissipated in the resistor is I squared R, and the rate at which energy is stored in the inductor is I VCB, which is Li di dt. So if we multiply this equation here, summing up all the voltages by I to give us all the powers involved, this means that part of the power, Vi, delivered by the source, is dissipated by the resistor, so that goes off to heat, and part is stored in here in the inductor. This is completely analogous to power analysis for a charging capacitor. So we've stored some here and some is dissipated. Now let's suppose switch S1 in the circuit has been closed for a long time, so that the current I equals V over R has been reached. So we're at this top value here, which is equal to V over R. What we're going to do now is close this switch S2 and open S1, and the moment we close S2, we'll assume that that's the exact same moment we open S1. We'll call that T equals 0. The current through R and L does not instantaneously go to 0, but decays smoothly as shown in this diagram. So now we can say that summing voltages around the loop, if we sum up, we get obviously the voltage over here plus the voltage over IR. So we're going to do that again. We'll sum up, we'll rearrange it, so we've got di minus RIL over dt. Then of course you can see here, now we'll be able to get I in terms of some function of t, because we can just integrate both sides. So we'll do that, and then we come all the way down here. We'll continue, so we go ln I, obviously we can, once you take the integral of 1 over I, you're just going to get ln I, and same for the other side, minus RLT. Now to find the constant, when t equals 0, we know that I equals I0, which is hence constant equals ln I. We'll place that back into 1, and then we just get ln equals this. We've got a log on that side, bring the logs together, again use the rule of logs. That's I over, that's the same, that there's the same as ln I over I0, which is here. So of course the log of a number is the power to which the base is raised, where natural log, the base is e, the exponential number, and we end up with I equals I0 e to the minus r over lt. We can just use this function now to evaluate any value of the current for any time. The time constant taught now is L over R, so you can see the time constant is L over R. It's the time for the current to decrease to 1 over E. You can see if you put L over R in there, then obviously that's going to reduce to minus 1, so that's just 1 over E. That's about 37% of its original value. So the energy needed to maintain the current during this decay is provided by the energy stored in the magnetic field of the inductor. So the inductor is causing this to happen. Yeah, it stored, remember at the last point, it stored all that energy, and the energy had to go somewhere, and that provided the current in the circuit, the release of this energy. We'll do the energy analysis again this time, and it's much easier. So what we're going to do now is we've summoned all the voltages up now. We've got 0 L di dt. We're going to multiply through by I to get the power. We end up with, just bringing this on the other side, I squared I equals minus Li di by dt. So in this case, of course, Li di by dt is negative, and this equation shows that the rate of decrease of energy stored in the inductor is equal to the rate of dissipation of energy, I squared I, in the resistor. So the energy considerations really shows how this works really quite well. When you remember that the inductor is holding energy when it's first charged up, and then eventually the current starts flowing, and then of course when you open S1 and close S2, then this energy that's been stored is then released.